I would like to begin today with a tale. Merry Christmas! Come, you're very welcome! You don't look very happy to be here, I must say. Anyway, I wanted to begin today with a tale. A tale of festive cheer. Although not really. Now, as many of you know, I have two lists. I have the nice list, and that's a very long list. And you'll be pleased to know that you're all on it, because you've been working very hard, coming to all of your lectures, and putting up with the drivel that your usual lecturer gives to you. But there's also a more unpleasant list, quite a sad, tragic list, for all the naughty boys and girls, and that's called my naughty list. Now, I got wind. Well, I don't know, I haven't eaten Brussels sprouts or anything. I got wind of some naughtiness here at Sussex University. I'd heard that a young gentleman living over in the Pevensey building was luring boys and girls with candy and pink hippopotami into a kind of concrete bunker, a little like this, in fact. And then when they were here, their eyes glistening for the candy, he would play the cruelest of tricks on them and teach them statistics and not really give them any candy at all. I thought, that's a terribly evil thing to do. Merry Christmas! That's a terribly evil thing to do. What I need to do is investigate. So I got on my sleigh and I flew all the way here to the campus and I went to pay him a little visit. I knocked on his office door. I went in. I thought, you know what? He doesn't look particularly naughty. Although he does have a kind of weird stare of someone with profound social awkwardness. But despite that, I thought he seems like a decent sort of chap. But nevertheless, you can't deny the stories. So I thought I'd take him off back to the North Pole, which I did. Now I thought I've got two courses of action here, and my first course of action is I could just simply put him on my naughty list. But I thought that seems far too good for him. So instead, I did something that I don't do very often, and I unleashed the Krampus. Are you aware of the Krampus? He's a kind of half goat, half demon kind of thing. And basically his job, he's sort of like an anti-Santa, if you like. His job is to punish naughty boys and girls. And he has a kind of basket on his back. And when he finds a naughty girl or boy, he sticks them in his basket, and he goes off and he gives them coal for Christmas. And nobody likes coal for Christmas. It's the worst Christmas present in the world. So I gave him to the Krampus. And off he went. His little head was sticking out of the bucket, looking all kind of sad and weepy. And I thought, that serves you right. Anyone who stands in front of people teaching statistics deserves to be a little sad and weepy now and again. And I waved him goodbye, and I wasn't going to give it another thought. But then a message came through from headquarters.
The gate, sir. Gate secured.
It just can't be. The system is foolproof.
There has to be an error, sir.
Error?
I spotted the ribbon glinting in the shadows, sir. I am actually trained in rapping, and I said to myself, Bryony, the rapping looks okay. Thank goodness. But that present should not be lying in the...
Thank you, soldier.
Someone got the wrong present. That's awful. Whose is it? No one gets the wrong present. 47785 BXK. Gift undelivered.
They got nothing. The child's been missed. Not necessarily. A child's been missed! You want to pick up the whole North Pole?
No idea. A child's been missed!
A glitch.
A glitch? You missed a child! They missed a child! Oh, my word! I was confused. I was panicked. I thought, this could never, ever happen again. But how can I prevent it from happening? I was all of a tiz. And suddenly, a little voice from the distance, from the bucket, said, Santa, I can help you. I thought, you, naughty boy, how can you help me? But nevertheless, I dashed over to the Krampus, and his little head, or not the Krampus, but the naughty boy, was popping out of the back, and he said, we can help you, Santa. I thought, well, I better hear him out. And he said, tell me about your operations. And I said, well, as you know, I have to deliver lots and lots and lots of presents on Christmas Eve. And that involves me being in a kind of superpositional state where I coexist in lots of places at the same time. That's essentially why children are not allowed to look at me, because if they do, then my probability wave collapses and I either exist or I don't exist, and that's a terrible thing to happen. But even that, even coexisting in lots of superpositional states is not enough. So I have to have a team of elves who help me do the deliveries. And he said, Santa, what happens on a typical delivery? And I said, well, you know, not everyone believes in Santa, and that's fine. So we visit everyone, and if they believe, then we give them presents, and if they don't believe, we sprinkle them with a little magic dust to hope that they have a nice year and everything goes safely for them. For the ones who believe, generally, they leave us treats. So typically, we'll slide into the house somehow, and then we'll look at the treats, and then, you know, we kind of eat them because it's rude not to. And you know what? He gave me a knowing look. And he said, treats? I said, yes, treats. Don't worry. They won't have any effect on deliveries at all. He kind of raised his eyebrow and said, really? I said, yes, well, of course they won't have any effect. I've spent 1 million and more years evolving a 4-dimensional stomach because I have to eat so many treats. And it's a bit like Doctor Who's TARDIS, except it's just as big on the outside as it is on the inside. But it means I can eat a remarkable amount of mulled wine and Christmas pudding. So it won't affect deliveries at all. And he looked at me and he said, but what about the elves, Santa? Ah! He was right! The elves! They're so small and they don't have 4-dimensional stomachs. Maybe it would affect their deliveries. But how on earth could I find out? And then he struck me a deal. He said, you know what, Santa? I can analyse your data for you. If you give me the data from last Christmas, I will get an answer for you as to what affects deliveries. I said, OK, well, that sounds good, because I really don't like numbers. But he said, but Santa, I need you to perform one last Christmas miracle for me. And I thought, well, I am Santa, I probably ought to perform a Christmas miracle now and again. So I said, what is it? And he said, think of my children. They have all come week in, week out to learn statistics. They've learned everything there is to know about the general linear model, apart from one final topic. Think of their sad, sad faces if they leave their module without knowledge of this final topic. Please, Santa, go and deliver the lecture for me. Well, I said, but I don't know a thing about logistic regression. And he said to me, don't worry, neither do I. I don't know anything about any of the lectures, but it doesn't stop me giving them. And I thought, oh, fair enough then, so here I am. Merry Christmas, one and all. So, our final topic is a festive topic. It's the festive topic of logistic regression. Now, logistic regression is a kind of linear model like all the ones that we've seen before, except you can use it when your outcome is categorical. And in particular, when your outcome is 2 categories. So imagine, for example, like me, you wanted to predict whether presents got delivered or not. That's a categorical outcome with 2 categories. The presents either got delivered or they did not get delivered. But there are other uses for it too. I just can't think of any off the top of my head. It's very useful in medical statistics, for example, if you want to predict the prognosis of someone based on various predictors. For example, so whether someone has an illness or doesn't have an illness. That's another good example of a logistic regression. Anyway, the data we had from our previous Christmas trip was we had some information about the types of treats that the elves ate, whether they ate Christmas pudding or mulled wine, and each elf only ate one of the 2 treats. We also have information about how many of the treats the elves consumed. So for each elf, they either consumed no treats, or 1 treat, or 2 treats, or 3 treats, or 4 treats. And remember, they only ever ate either Christmas pudding or mulled wine. The other bit of information we had is whether the presents got delivered or not. So our outcome variable is a category with 2 categories, delivered or not delivered. Now, imagine we've learned all about linear models this term, and imagine we were to fit a standard linear model to these data. It would look a bit like this. Now, hopefully this seems familiar, because otherwise I don't really know how to explain it, because I'm Santa. If we were to treat this as a standard linear model, imagine we had some kind of outcome that was continuous, like how long it took us to deliver things. we'd have that outcome and we'd predict it from a predictor variable. And let's keep things simple for now and just focus on the treats. Mince pie, Christmas pudding or mulled wine. Now we have a beta value attached to that predictor that tells us about whether that predictor predicts the outcome. And in this case, if we had Christmas pudding and mulled wine as a predictor, then that beta would tell us something about the difference between the mean delivery times. But we don't have delivery times, we just have this categorical variable. They were delivered or they weren't delivered. Now this creates a problem, because although we can conceptualize the model in exactly the same way, so we could treat as a categorical predictor, we could dummy code it with zeros and ones. Let's say, for example, we could use 0 for our Christmas pudding condition and make it the baseline, and we could use a 1 for mulled wine and make it not the baseline. But the big problem we have is that this is going to violate our assumption of linearity. Now, you might remember from earlier on in the term, we said it was very important that the relationship we were trying to model was in fact linear. But it can't be linear with a categorical outcome, can it? So we can't fit the model that we've been fitting all term. What we can do instead is adjust the model slightly, and we use something called a logit link function. Doesn't that sound like an exciting thing to get for Christmas? I often wonder why I don't get more children coming to see me and saying, all I want for Christmas Santa is a logit link function. But they don't. They just want cars and castles and teddy bears and PlayStations and drugs. But anyway, so we can use a logit link function. Now what does this do? All this does is it changes the form of the model slightly. But essentially, we're doing a very, very similar thing. Now, if I can get this pen thing to work, I'll show you how. Where is the pen? Oh, there's the pen thing. Oh dear, the pen thing's not working. Oh, now it will work. Lovely, lovely. Right. So what we're doing, by applying this link function, is instead of predicting whether something was delivered or not, we predict the probability of delivery. You could even spell it correctly if you like. So the probability of delivery is predicted from this other equation on the right-hand side. And although it's a complex-looking equation, the main thing to note about it is that the standard linear model is contained within it. So although we've jigged things around a little bit, we've changed the form, we are actually still using a linear model, but we're using it to predict the probability of delivery rather than the actual score itself. So this is one way to conceptualize things. A different way to conceptualize it, which some people find easier, and it's exactly the same equation, but it's just rearranged. Try that at home if you like. Is to do this. So all we have done is made the linear model the subject of the equation. So we've shifted everything around, moved some things over to the other side, leaving us just with the linear model that we know and love on this side. The question is, what does this leave us with on the left-hand side? Well, on the top of that little fraction is the probability of the outcome, so the probability of delivery. And on the underside of it is 1 minus the probability of delivery. And because probabilities have to sum to 1, the bottom half is just the probability of not being delivered. So we've got the probability of delivery divided by the probability of not being delivered. And that's known as the odds, which we'll talk about a little bit in a minute. And they are contained within some brackets, and outside the brackets is the log function. So what we end up predicting are the log odds, which nobody understands. But I'm going to try to give you an idea of what the odds are to help. So, again, we're just fitting the standard linear model, but the outcome is the log odds of the outcome occurring, rather than the actual score of the outcome, because we don't have scores, we've got categories. But otherwise, what we're doing is effectively the same as with any other linear model. We've got the same linear form, we've got a beta 0, we've got predictors, each predictor has a parameter attached to it. But we're predicting log odds rather than the actual score, because we have no scores in the outcome. So our betas start to represent slightly different things, but the main thing is to focus on the fact that the form of the model is the same. So, what are log odds? And what are odds? Let's have a look. Here's a classification table. So this is just all of our elves divvied up into 4 different boxes. So there's the elves who ate Christmas pudding and successfully delivered. 150 of them. There's 28 elves who ate Christmas pudding and unsuccessfully delivered. And then there's 100 elves who had mulled wine and successfully delivered, and 122 who had mulled wine and unsuccessfully delivered. Now, if we wanted to compute the odds of delivery, it is a simple matter. The odds of delivery are simply the number of successful deliveries, the number delivered, relative to the number not delivered. So, we're ignoring the Christmas pudding and mulled wine for the time being, although those values will come in handy in a minute. We're just saying how many were delivered relative to how many were not delivered. And that is the odds. The odds of delivery are the number delivered against the number not. So it's 250 divided by 150 gives us 1.67. So this means 1.67 times more presents were delivered than not delivered. That is what the odds are. So in our model, this is what we're predicting, except we're predicting the log of that value, which confuses things enormously because, like I said, no one really understands what logs do. So often we don't deal with the actual betas, the actual parameters themselves, because the parameters refer to log odds, and we don't like log odds. We often refer instead to something called the odds ratio. Now, the odds ratio just tells us something about how odds change. So if we know what odds are, an odds ratio is really about how odds change as a function of something else. So let's have a look at how our odds change as a function of which treat people had. So first we can calculate the odds of delivery after Christmas pudding, and then we can calculate the odds of delivery after mulled wine. So the odds of delivery after pudding are the number delivered after pudding divided by the number not delivered after pudding. We can grab these values from the table. It's just going to be 150 were delivered and 28 not delivered. Which gives us 5.36. That means after eating Christmas pudding, 5.36 times more presents were delivered than not. That's the odds of delivery after pudding. What about for wine? After mulled wine, 100 presents were delivered, but 122 were not. 122 unsuccessful deliveries. Which gives us an odds of 0.82. Now, a very important thing here is this value is less than 1. But the odds of delivery after pudding are more than 1. Now, if you think about it, if the value was 1, that would mean the number delivered was exactly the same as the number not delivered. In other words, it would be equally likely that a delivery would happen or not. If a value is more than 1, it means that it's more likely to happen than not. So more presents were delivered than not. And if it's less than 1, like it is for wine, it means the opposite. It means that more unsuccessful deliveries happened than successful ones. So an odds of 0.82 means that after wine, it was more likely that presents wouldn't be delivered than they would. So you can see after eating pudding, it's more likely the presents will be delivered. After eating wine, it's less likely they'll be delivered. So we can look at the change. We can look at the relative change. That's what the odds ratio is. It's the odds of delivery in one condition or after one thing. So the odds of delivery after wine divided by the odds of delivery after pudding. And this value turns out to be very small. And what that means again is that as we move from eating pudding to eating wine, the odds of delivery go down, they shrink. So in other words, it becomes less likely the presents will be delivered than less likely that they will be delivered. So odds ratios under 1 tell us that as something changes, the outcome becomes less likely. Whereas an odds ratio of 1 tells us that as something changes, in this case as treat changes, nothing happens to the odds, they stay the same. And a value greater than 1 tells us that as the thing changes, as pudding changes to wine, the odds of delivery would go up. So that's what an odds ratio is. Now, remember this value and remember this value, for they are magical values that will come up again. Now, when you do a logistic regression, as well as getting your betas, as well as getting your parameters, you get this thing called xb, the exponent of b. And the exponent of b is what I was just talking about. It's the odds ratio. So it's the odds after a unit change in the predictor, divided by the original odds. So in other words, if we started off with a predictor that was pudding, so our treatment condition, our baseline condition, our treat condition was 0, pudding, and that changes to wine, it's asking the question of, as pudding changes to wine, what is the change in the odds? And that's what the beta associated with treat would represent. So in our model, we have a beta 0, a constant, if you like, intercept, if you want to call it that, although it doesn't make quite so much sense to call it that in this context. And that will be the log odds of the outcome when the predictors are 0. Now, in this case, when we only have treat, it means the log odds when treat is 0. But it's easier to interpret the exponent of that. So to get rid of the log, we reverse it by using the exponent. And that gives us the odds of the outcome when the predictor is 0. So our beta 0 is going to be the odds of the outcome in the pudding condition. So that was that value on the screen before, 5.36, I think it was. Beta 1, on the other hand, so the beta associated with treat, associated with the predictor, tells us how the odds of the outcome, how the log odds of the outcome change as the predictor changes by a unit. So in the case of our treat example, as pudding changes to wine, how much does the log odds change by? But again, we get rid of the log often and just refer to the xb, which is the exponent of the beta, and that then expresses it in terms of odds. So it tells us the change in the odds of the outcome associated with a unit change in the predictor. And as I've just said, if the odds ratio is greater than 1, it means as the predictor increases, as we go from pudding to wine, the probability of the outcome occurring increases also. If the value is less than 1, it means the opposite. As we go from pudding to wine, the probability of the outcome occurring decreases. And if it is exactly 1, it means no effect whatsoever. As we change from pudding to wine, the odds of delivery are exactly the same. So, when we do all this in SPSS, we will get some output. First of all, we'll get something that tells us about how our outcome is coded. For example, it tells us that delivered has a code of 1 and not delivered has a code of 0. So that means that helps us to interpret the outcome. I mean, generally speaking, you want your success category to be coded as 1 and your non-success category to be coded as 0 because it's much easier to interpret things. For your predictor variable, you will similarly set things up, hopefully, so that your control group, if you have one, has a code of 0 and non-control groups have codes bigger than 0. So you can set up categorical predictors in exactly the same way as any other linear model. So use dummy coding, 0s and 1s. You'll get an R² value, which is comparable to the R² value in an ordinary general linear model. So this one tells us, for example, that about 21.5% of the variation in deliveries is accounted for by treat, the type of treat, quite a large amount. But more important is we get a table rather like all the other linear models. And we'll get some beta values like this. These, as I said, represent the change in the log odds. But because they don't make an awful lot of, log odds don't make an awful lot of sense to people, often we focus just on the exponent. So we convert these log odds back to their original units of measurement, back to odds. Now, these two values should seem a little bit familiar. So the value for the treats consumed, the exponent of b is 0.153. Now let's go back a few slides. No, that's forwards. So confusing, because I basically exist outside of the concept of time. Anyway, that value, the odds ratio that we calculated earlier, 0.15, and look, that's the value we get in our output, 0.15. So what this represents is the change in the odds of the outcome as our predictor changes from pudding to mulled wine. So we know the odds go down. Basically means that deliveries are, there are fewer deliveries after mulled wine than there are after Christmas pudding. And the XB for the constant, the XB when all the predictors are 0, when treat is 0, we're in the pudding condition. So that's 5.35 is the odds of delivery in the pudding condition. And again, let's backtrack. It's this value here that we calculated. So it's just the odds of delivery in the group coded as 0. Now, what if we want to add multiple predictors? Well, then things get very, very tiresome indeed. Now imagine we had quantity, we measured quantity, and let's say we want to put in the interaction between quantity and treat as well. Well, we do what we would normally do in a linear model, which is we add in quantity and we give it a parameter, and then we add in the interaction and we give it a parameter. But again, just bear in mind that we're not actually using this form of the equation. We're using a slightly different form. Like I said, most people will be more comfortable probably with this characterization of it, because the right-hand side doesn't change. It's just like any other linear model we fitted. But again, I just draw your attention that instead of predicting the score on an outcome variable, because we don't have scores, we've got categories, we end up predicting the log odds of the event occurring. So the log odds of delivery. But otherwise, it's very much the same as all the models we've been dealing with before. When you have multiple predictors, you can build the model in exactly the same way that you did for any other general linear model with lots of predictors. You can use forced entry, which we know is terrible. The only person allowed to use forced entry is Santa when he's delivering presents. And I try not to be too forceful. I try to just slide down the chimney or maybe sprinkle myself with fairy dust and climb through the dog flap or something. You can use a hierarchical method. This is the best method because this means that you're entering variables based on past research and you're doing it in a theoretically motivated way. Finally, if you really want to upset Santa and get yourself on his naughty list, you can use stepwise methods, which is where you enter variables based on some statistical criterion. So in other words, if the predictor is going to significantly improve the fit of the model, it gets chucked in, and if it's not, it gets chucked out. So again, nothing has changed. It's exactly the same as the general linear model, apart from the outcome that we're predicting. Things that my voice, that can go wrong. Other things that can go wrong. Similar things to what we've seen before. So we had this assumption of linearity. Now, all we've done by using this logit link function is we've made a kind of dichotomous relationship into a linear one. So that's effectively the effect that it has. So we still have this assumption that once we've converted to the logit, that logit should also have a linear relationship to the outcome. And there are various ways to test that, but it's essentially the same assumption as before. We've seen before there's an issue of having spherical residuals, and in particular this means that your errors, your residuals of the model should be independent, so you shouldn't have repeated measures, for example. The same thing applies here. There are more sophisticated versions of logistic regression that you can use that handle dependent errors, but we're not going to teach you about them because they're hideous. For this particular kind of logistic regression, though, you need independent observations and therefore independent errors. Also, there's a problem of multicollinearity. What if some of your predictors are very highly correlated with each other? Well, that's just going to mean that you can't reliably estimate any of your parameters, so that's bad news too. These are all things we've seen before, but there's a couple of new ones as well. When we have a binary outcome like we have here, there are two unique problems. The first is known as incomplete information, and the second is known as complete separation. Now, to illustrate incomplete information, I want you to consider our data table. So we have quantity consumed, and we have Christmas pudding versus mulled wine, and we have delivered versus not delivered. And if you combine all of those categories, so all of the values of quantity, 1, 2, 3, and 4, and 0, repeat that for mulled wine, and then you need data for how many were delivered, how many presents were delivered, or how many deliveries were successful, and how many were unsuccessful. You end up with 20 cells, 20 design cells that you need some data in. Now imagine we had a situation like here where no elves had 2 quantities of Christmas pudding and successfully delivered. We've got a missing cell, missing data. Same, imagine we had no elves who had 4 helpings of mulled wine and didn't deliver. Now, these gaps in the table create problems. It becomes very difficult to estimate the parameters when you have these empty cells. So incomplete information relates to this possibility that you have gaps in your design. You might think, well, this is not too bad. I mean, we should be able to fill all of our cells and everything. But imagine that as well as quantity, we measured the elves' BMI. We measured their kind of size, because that should affect what effect the treats have. So imagine we might have, I don't know what the average elf BMI is, but anyway, let's say we had BMIs of like 20, 21, 18, 24, 25, whatever. We'd have lots and lots of values, and then for every single one of these, so for all 20 of these cells, we would need 20 cells for every value of BMI of an elf that we observed in the data. So when you have continuous predictors, this kind of, the gaps in the data become, they magnify very, 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 very quickly. Few gaps is fine, but if you start having too many gaps, essentially your standard errors are going to go haywire. So watch out for that. Now, for complete separation, I'm going to bring you back to the Krampus. This is the Krampus. If you Google Krampus, you can find some very much more unpleasant pictures than that. I decided to choose a fairly sedate one. There they are, little children in his bucket. I would say one of them was your lecturer, but they've all got far too much hair to be him. Anyway, complete separation. Now, imagine a situation. Coming up to Christmas, you're someone who celebrates that sort of thing, and you're a little worried that you've maybe been slightly naughty. Maybe you missed one of your lectures, and you're thinking, that might be sufficient to get me on the naughty list. And if I'm on the naughty list, then the Krampus might come round. So you decide you're going to outwit Santa by creating a device that's going to tell you whether a Santa has entered your house or a Krampus. A kind of pressure pad, if you like. Now what you do is you get some data. Now, like I said, I exist in lots of superpositional states, and each Santa who exists is slightly different in size, because it's very, very difficult to maintain several coexisting versions of myself. So they vary in size a little bit. So you've got some weights of Santas, and you've got some weights of Krampuses. And it looks a bit like this. So each triangle is a Santa who you've weighed. So Santas weigh somewhere between about 98 kilos and, say, about 145 kilos. Now, Krampuses are big and muscly, so they weigh a little bit more on average. But there's a lot of overlap between Santas and Krampuses. The lightest Krampus weighs in at about 125, and the largest or heaviest Krampus weighs in at about 154-ish. So you've got this overlap. What you can do, because you've got your pressure pad, you've got some data, you decide, I'll fit a logistic regression model to help me work out the probability curve of whether something is a Krampus or a Santa, based on weight. And this is the probability here, vary from 0 to 1. So 0, absolutely not a Krampus. 1, definitely a Krampus. And this red line is the curve in between the two. So what you can do, at 0.5, that's an equal chance of being a Santa or a Krampus. And you can work out the weight. So you can say, well, if it weighs about 133, that's the tipping point at which it becomes more likely that it's a Krampus than a Santa. So if you set your sensor to be at about 133, so at that point, anything heavier than that, it rings an alarm bell in your head, and you can wake up and run quickly away from the Krampus. That's all well and good, but now imagine that you're on the elf's route rather than Santa's route. So you've weighed some elves, and they're all quite small, so the heaviest elf is only just over 40 kilos. And the Krampuses weigh about the same as they did before. So that's the range of Krampus weights. Now there's this big gap in the middle. There's a gap in the middle where there's no data at all. This is known as complete separation. You can perfectly predict whether something is a Krampus or an elf. If it weighs less than about 50 kilos, it's an elf. If it weighs more than 100 kilos, it's a Krampus. You've got complete, perfect prediction. Now the problem with this is when you've got this scenario is you can't estimate the curve in between. So basically the logistic regression breaks down. because it's trying to estimate what that curve should be, and it's got no data in the middle on which to do it, so it goes into a frenzy until it basically explodes. It doesn't really explode, but what it does is it gives you this kind of very vertical curve like this. But the problem is that vertical curve is no more realistic than this dotted curve. So essentially, your model is a kind of nonsense. So again, if you get very, very large standard errors, make sure you don't have complete separation. Make sure you can't perfectly predict your outcome. Right, so if we fit this model in SPSS, we've got these two extra predictors, quantity consumed and the interaction. Our R squared has gone up from 0.2, whatever it was, 0.21, up to 0.4. So it's improved. Where the fit of the model is better, if you like. So it's, we're predicting a greater proportion of variation in deliveries. We can look a little bit at how accurately presents are classified, how accurately deliveries are classified by the model. And you can see the percentage of cases that are correctly classified is about 80%. That's pretty good. Pretty good. 4 out of 5 cases are correctly classified by the model, so it's a reasonably good fitting model. What about the parameters of the model? Well, we've got a table again, just like we do with any other linear model. We've got some betas. These tell us about the change in the log odds as a result of a unit change in the predictor. But probably most of the time we'll stick to interpreting the exponent of b, because that's in that's in odds units rather than log odds. You also have significance values just like you would in any other model. So we can see, for example, here, treat consumed on its own does not significantly predict the outcome. Quantity of treats consumed does not significantly predict the outcome, but the interaction does! Huzzah! So we have this interaction term here. It's very significant, and it has an XB of 0.358. Now, what does that mean? Well, before we get into that, I just want to flag that you can bootstrap these parameters just like any other model. I'm not going to get into this, but it's just to alert you to the fact that you can. We can again look at how well the model is classifying cases if you want to identify particular cases that are badly classified. So essentially this is a 0.5 probability, so we would like D for delivery. All our Ds should be on this side, and non-deliveries should all be on this side. So this tells us cases that are misclassified. So it's something that can be useful alongside that little table that I put up. I'm teasing you here though, because this is not the main thing. You can look at residuals or kittens. Shall we look at the kittens or the residuals? Residuals. No, kittens. Kittens. No. Oh, residuals. The residuals win. Again, we've got these standardized residuals. Interpret them in exactly the same way as any other linear model. This is nothing new. You just interpret them in the same way. So you'd expect roughly 5% of them to be outside of a value of about 1.96 when you ignore the minus sign. And likewise, you wouldn't expect too many values to be above about 3. So we have a couple of values above 3, but the overall sample was 400 or so, so that's probably about fine. Now, how do we interpret this interaction? Well, what I've done here is I've plotted the number of deliveries in red and superimposed on top the number of non-deliveries in green. Now, if we look at mince pie, what you want to do is look at the relative height of the red and the green bar. So if the red bar is much higher than the green bar, it means there were many more delivered than not delivered. And you can see for mince pies, across all of the quantities of treat, always more presents were delivered than not. The red bar is always higher than the green bar. Although, relatively speaking, after 4 treats, the relative heights of the red and green are getting closer together, but still, always more delivered than not. When you look at the mulled wine side, something very interesting happens. For 0 and 1 treat, more presents are delivered than not. The red bars are higher than the green. But when 2 or more treats are eaten, it reverses. The pattern reverses. There are more presents not delivered than delivered. So the pattern reverses for mulled wine at 2, 3 and 4 treats, but that doesn't happen for mince pies. That's what the interaction is effectively telling us. Now, we can have a look at this in a slightly different way. So what I'm going to do is I'm going to look at the effect of quantity for mince pies only, so in the mince pie group only, so only elves that ate mince pies, and then I'm going to do the same for the mulled wine, only the elves that had mulled wine. So look at the effect of quantity. Now, for those that ate Christmas pudding, I keep saying mince pies, don't I? I'm quite obsessed with mince pies at the moment. For those that ate Christmas pudding, that's the change in the log odds associated with quantity. It's basically 0. So basically, quantity has pretty much no effect for Christmas pudding. And if we look at the exp-b for that, it's basically 1. There's no effect. However, for mulled wine, quantity of treats has a negative effect. So in other words, as quantity goes up, the log odds of delivery go down. And again, this is reflected by an exp-b that is much smaller than 1. So it means as quantity goes up, the odds of delivery go down. So for Christmas pudding, not a lot happening. For mulled wine, the odds of delivery decrease. Now what happens if we look at the difference in the betas? So if we take the beta in the mulled wine condition, and we subtract from it the beta for the Christmas pudding condition, we end up with this value. This is the difference in the beta. This is the change in the beta that results from going from Christmas pudding to mulled wine. And if we take the exponent of that difference, then we end up with 0.358, which is the value that we got here. So, what the odds ratio for the interaction is telling us is basically that as we go from Christmas pudding, as we go from Christmas pudding to mulled wine, the odds of delivery go down. This graph also illustrates this. So what I've done here is rather than plotting delivered and not delivered, I've just converted to a percentage. So the percentage delivered. So 100% would mean all deliveries successful and no deliveries unsuccessful. Now we just saw that the beta in the Christmas pudding condition was minus 0.081. It was basically 0. And although this doesn't map exactly to this line, it shows you roughly what that line represents, which is that very little change at all in delivery rates, in the percentage delivered, as a function of the quantity of treats. That red line is quite flat. Whereas, in the mulled wine condition, that beta, so the change in the log odds, was negative, which reflected the fact that as quantity of treats went up, the odds of delivery went down, or the log odds of delivery went down. So what we're seeing in the interaction is essentially there isn't a difference between delivery rates for after Christmas pudding and mulled wine when they eat nothing, as you might expect, because they're eating nothing. If they have one of the treats, again, no real difference. Doesn't matter whether they eat Christmas pudding or mulled wine. However, at 2 treats, we start to see the effect opening up. So all of a sudden, the percent delivered plummets for mulled wine, but it doesn't plummet for Christmas pudding. It plummets again after 3 treats. Big difference there, and again, that difference is maintained for 4 treats. So essentially, this interaction is telling us that the change in the log odds, the rate of change is different for Christmas pudding and mulled wine. For Christmas pudding, flat as a pancake. For mulled wine, going down. The more treats you eat, the less presents get delivered. Right, how are you going to remember all of this? It's very complicated, isn't it? The best way to remember anything about statistics is with a song. And I have a very festive song here to help you remember all of this information.
You better watch out, you might want to cry, you better beware, I'm telling you why. Logistic regression is coming to town. Santa's checking the output, he's checking it twice to try to predict who's naughty or nice. Logistic regression is coming to town. He's got a binary outcome, residuals aren't normal, but with a logit link function, everything is cool, so there's nothing to fear, there's no need to cry, it's like every other model we've tried. Logistic regression is coming to town. The effect of predictors is easy to see, you just need to check the exponent of b. Logistic regression is coming to town. But design cells can be empty, that's incomplete information. And if prediction is perfect, then you have complete separation. But there's nothing to fear, there's no need to cry, it's like every other model we've tried. Logistic regression is coming to town. Logistic regression is coming to town.